Hello all, we are starting on chapter 5 today. Chapter 5 is on gases. So the first topic in chapter 5 we're going to go through is interconverting atmospheres and torr and some other units of pressure. So this will feel familiar to what we looked at in chapter 1 because we're going to do various unit conversions. We might have millipascals or kilopascals or different variations of atmospheres and torr. So let's go into this topic now. To build up to this topic, I do want to show you this periodic table. So these colored elements here in sort of the teal color, not in the purple color, those are elements that exist as gases at 25 degrees Celsius. So at 25 degrees C and at 1 atmosphere, that's our typical ambient environmental temperature and typical pressure. So 1 atmosphere and pressure is sort of a standard pressure. 25 degrees C into Kelvin. Do you remember what we need to get this into Kelvin? So plus 273.15. So you may recognize that this group here, remember these vertical columns are our groups. So group 8A are the noble gases. So those definitely exist as gases. This is not a surprise. They exist as gases around ambient temperature and standard pressure. Then some of our Brinkelhoffs as well shouldn't be a surprise. Although technically bromine and iodine don't exist as gases at 25 degrees C and at 1 atmosphere. So as a refresher on those Brinkelhoffs, these exist as diatomics. So bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. The Brinkelhoffs, so you should recognize these here on the periodic table. These noble gases just exist as usually monatomic gases or monatomic atoms, so xenon, helium, etc. These don't exist as diatomics, they just exist as their atomic form in a gaseous state. So as was mentioned here in table 5.1, some of these should be familiar. So some substances found as gases at 1 atmosphere of pressure and 25 degrees Celsius. So here's hydrogen gas, diatomic oxygen, diatomic fluorine, and then some of our noble gases. Notice they're not diatomics. They just are a monatomic element that exists as a gas. Ozone's another example. So 3 oxygen atoms bonded to one another. So ozone exists as a gas at this temperature and at this pressure. Here's some other compounds as well, just to be aware of. So something you might recognize is like carbon dioxide. That exists as a gas at this temperature and pressure. Carbon monoxide, methane gas, sulfur dioxide, etc. Now, going back to chapter 1, we talked about different physical states of matter. So now some properties of gases. Remember, we could have solid, liquid, and gas. So gases are unique because they assume the volume and the shape of their containers. Whereas we know for liquids, the liquid molecules will sort of be at the bottom of a container. They're not going to float up and fill the space of the container. Gases, however, they will. They will assume the volume and the shape of the container that they're in. Also, because gas particles are spread apart relatively more than particles of a solid or a liquid, gases then are the most compressible state of matter. So some ozone particles might be spread about like this. So because gases are spread apart from one another, they can be more compressible. So we can force this ozone molecule to be closer in proximity to this one as well. But for a liquid or a solid, the particles are already somewhat close to one another. So like liquid particles are already somewhat close to one another. They're not as compressible as gas particles. Solids are even closer to one another compared to liquids and then compared to gases. So NO2 gas, for example, we can see it occupies the full volume and the full shape of this volumetric flask that you may have seen now in the lab. So gases like nitrogen dioxide, for example, they will also mix evenly and completely when confined to the same container. So think about air, think about capturing some air, trapping some air in some container. The nitrogen that's present, the hydrogen that's present, those gases will mix evenly and completely when confined to the same container. However, for a solid or something like a metal alloy, you might have some copper metal and some nickel metal. They won't evenly mix necessarily, right? We could have a solid that has some concentrated portion of copper, then some concentrated portion of nickel. But for gases that are mixed, they will evenly disperse throughout the container and evenly mix. We won't have some concentrated pockets of H2 and then some other concentrated pockets of O2, right? Those will all mix together and evenly with one another because these are gases and that's a property of gases. Now this next property, gases have much lower densities than liquids and solids. We remember that density represented by rho or lowercase d. Density is a mass over a volume. If we take the same volume, for example, and we put some gas particles into that volume and we measure the mass, there's not going to be as many gas particles within one space of volume compared to a solid or a liquid of that same volume. Right, for a solid, there will be a lot of these solid particles within one shape or within one volume. So that's going to have a higher density than liquid particles that are more spread out than solid particles. There's less mass for a liquid within a specific volume compared to a solid within that same specified volume. Then for gases, they're even more spread out. They're way less dense. There's less mass per unit volume for gases. Now we think of units of pressure being pressures in atmospheres, pascals, torr. To fully understand pressure, a good way to think about it is that pressure is actually equal to a force over some unit area. For example, we'll talk more about pressure, but you could imagine some ozone particles as they're moving about, some ozone gas particles, they're moving about in this vessel. And pressure will be applied to the sides of the container from those gas particles. So if we think about these gas particles applying some pressure because they're moving about this vessel and hitting the sides of the container. How we can picture this now is it's really a force applied by the gas molecules over some unit area that those gas particles are applying force to. So that's one way to think about pressure. We kind of think about pressure conceptually, but not always as far as a force per some area. But that is what pressure is defined as. So for pressure, we can have pascals. That's really the same as a Newton per meter squared. If you recognize a Newton from one of your past classes, it's a measure of force. So pressure can be in pascals. This is the same thing. 1 pascal is equal to 1 Newton per meter squared. We also commonly see atmospheres. So 1 atmosphere of pressure is equal to 760. This is millimeters of mercury. Millimeters of mercury, that is a unit of pressure we often see, and we'll talk more about that in this visual here. These both are equal to 760 torr. So 1 millimeter of mercury from this conversion factor stated here must be equal to 1 torr. 1 atmosphere is also equal to 101.325 pascals. You might also see kilopascals as another common unit of pressure. So 1 atmosphere, 101,325 pascals. So this pressure unit for a millimeter of mercury, so how we can think about that is that something is applying pressure, be it the atmosphere, be it gravity applying pressure. As pressure is applied here, the level of mercury rises. So this pressure can be thought of then as in units of how much the mercury level is rising. We measure the level of mercury rising as far as how many millimeters of mercury this level is changing, right? So if we apply some pressure and then the millimeter mercury level goes up some amount, that's also how we can think about pressure. So yes, this is technically a distance amount. How many millimeters is it changing? But based on the properties of liquid mercury, we can make millimeters of mercury into a unit of pressure that happens to be equal to 1 torr, or also we can convert millimeters of mercury into units of atmospheres or pascals, etc. So here's a little bit more explanation on what I was saying. Using one of these devices, we'll come back to looking at different levels of pressures in millimeters of mercury and in atmospheres in a little bit later of a topic in chapter 5. Then another way that's interesting to think about pressure, especially if you're into studying weather or thinking about the weather, if we think about a column of air starting at wherever we are, then extending upwards into space and further away from the planet, then of course the pressure we feel here is going to be a lot different than the pressure we'd feel some distance away from the Earth's surface. So we think about this air that's pushing down on the Earth's surface. If we're down here on the surface of the planet, we will feel a lot more pressure than we would feel if we were some further distance away from the surface. So all of these air particles are sort of pushing down, pushing down, pushing down, to then what we feel down here is a lot of pressure on the surface of the Earth. But we're used to feeling that pressure. It's what we feel every day as we're walking around. So air is more dense near the Earth's surface, while air is far less dense in the upper atmosphere. There's less air pushing down on the spot that we're taking that pressure. So less pressure felt at this distance, but then a lot more pressure felt at this distance because it's all these air particles pushing down. Those air particles pushing down are what cause us to feel pressure on the Earth's surface. So when the air is more dense, so even considering if we're on the planet's surface itself, we know that air density can change based on the weather. Atmospheric pressure is greater, so there's a greater pressure when the air is more dense. So atmospheric pressure is greater at sea level than at distances further from sea level. So we'll feel more pressure here at sea level than we would feel if we climbed up a mountain, for example. This applies too for different inclines, different altitudes throughout the globe. So the higher up we are, the less pressure. The closer we are to the Earth's surface, the more pressure we feel. So let's go into these different units of pressure. The pressure inside a high vacuum chamber is 0.000100 millimeters of mercury. We're going to calculate the gas pressure, convert this pressure into both atmosphere and into torr. So these conversion factors are ones that you should write on your note card or start memorizing, but there's a few key ones we need to know so we can go between atmospheres, pascals, torr, millimeters of mercury, etc. One thing I want to point out is that our standard unit, the SI unit of pressure, is a pascal with the symbol PA, capital PA. Now, while that is the standard unit of pressure, we don't always see it measured in pascals. More commonly, we'll see atmospheres, so atmosphere denoted as ATM, and then in torr, or TORR. So 760 torr is the same as 1 atmosphere. 1 atmosphere is the same as 101,325 pascals. What if we want to convert pascals into kilopascals or kilopascals? Well, we haven't dealt with pascals yet, but we definitely converted between grams and kilograms. We've used that kilo as a prefix. So for every 1,000 pascals, that must be the same as 1 kilopascal. So we divide this by 1,000 or move the decimal point over 1, 2, 3. So now 1 atmosphere is actually the same as 101.325. What unit now? This is in kilopascals. Next, a really important thing to keep in mind is that normal standard atmospheric pressure at sea level is just about equal to exactly 1 atmosphere. So normal atmospheric pressure is actually about 1 atm. So now here's millimeters of mercury. So 1 millimeter mercury is equal to 1 torr. We saw that up here. So here's 760 millimeters of mercury is equal to 760 torr, but we know that's really the same as 1 millimeter mercury is equivalent to 1 torr, right? These are equivalent. In weather forecasting, we might see millimeters of mercury, or millibars is actually pretty common. So some other conversion factors, we have this one, and 1 millibar is equal to 100 pascals. So you could imagine we might take millibars into pascals, take pascals into kilopascals, take kilopascals back into atmospheres, back into torr, etc. So we should get comfortable using all these different conversion factors and keeping track what we learned in chapter 1. So using that prefix kilo, this prefix milli if we need to. So let's practice now and let's solve our practice problem. Based on the conversion factors we saw on the last slide, we know normal atmospheric pressure at sea level is about 1 atmosphere. During the conversions, we could figure out that that's the same as about 760 millimeters of mercury, or 1013.25 millibar. How do we get that millibar conversion? Well, 1 millibar is 100 pascals. So starting out at 1 atmosphere is the same as 101.325 pascals. Then for pascal to millibar, for every 100 pascals, that's 1 millibar. So then doing this conversion factor, that's how we get the fact that 1 atmosphere is really equivalent to 1013.25 millibar. So you should feel comfortable doing these different various pressure conversion problems. Now to go from millimeters of mercury into atmospheres, we can use a series of the conversion factors that we know and then how to get into atmospheres. Well, firstly, 1 millimeter of mercury is the same as 1 torr. Then we have this conversion factor to go between torr and atmosphere. We also have this conversion factor, right? So 1 atmosphere is the same as 760 millimeters of mercury. So get comfortable using whichever conversion factors work for you. To be safe, you can take it step by step and go from first into torr, then into atmosphere. Again, just find what works for you. So we know for every 1 millimeter of mercury, that's equivalent to 1 torr. So if we want to cancel out millimeters of mercury, then we put millimeters of mercury here in the denominator and then torr here in the numerator. Then between torr and atmospheres, the conversion factor is that for every 760 torr, that's 1 atmosphere. So for every 760 torr, that's equal to 1 atmosphere. Do we put atmospheres in the numerator or atmospheres in the denominator? We want to end up with atmospheres as our final unit. So we want to cancel out torr. So put 760 torr, 1 atmosphere. This leads to torr and torr canceling out. So basically taking this pressure in millimeters of mercury initially divided by 760 equals, so 1.32 times 10 to the negative 7th atmospheres. So putting this with 3 sig figs like we were told to do, and then putting it into scientific notation. It's easier to see a value like this instead of seeing a bunch of zeros out front. So we're going to report this in scientific notation, again, because it's easier to visualize without all those zeros out front. Then we were also asked to convert this into torr. So we have that. We just need to not do this next step here. So 0.000100 millimeters of mercury to go between millimeters of mercury and torr. Technically, it's a 1-to-1 conversion, so we don't really need to show this, but it's good to get practice figuring out what we need to cancel out. So we need to put millimeters of mercury in the denominator here. This cancels out, this cancels out. Then we just have torr in the numerator. That's equal to this same number here, right? So 1, 2, 3 zeros here, 100. Those are our 3 sig figs. Then we figured out this is in units of torr. Here's our final answer for this practice problem. I do want to encourage you to check out 5.1 and 5.2 in the main slide deck to practice going between atmospheres, millimeters of mercury, pascals, kilopascals. So get more practice looking at the problems in the main slide deck. Next topic here is understanding pressure, equilibrium, and atmospheric pressure. So within this topic, we're going to be focusing on these manometers. So let's go through first a closed tube manometer. It's a closed tube manometer because this portion is closed here. We'll look at a next example where this is not a closed manometer, but in a closed tube manometer, liquid mercury is in a U-tube, not to be confused with U-tube, but in a U-tube is the same on both sides of the U. So this U-tube here, mercury is on both sides of this U-tube, or on both sides of this manometer, whichever you prefer to say. When a gas sample is open to the mercury in the tube, the mercury in the U-tube is pushed into one side of the U. So this gas sample here is then opened to the mercury that is still contained on both sides of the U. Initially, the level of mercury might have been somewhere here or up here, depending on what was in this gas vessel initially. But here we have a gas present. When that gas starts to move about in the manometer, it's going to move this direction, forcing the millimeters of mercury to increase on this side. So it's pushing the mercury to this side. It's applying pressure to mercury. So we know from that unit of mercury we've been looking at so far, it's increasing the pressure, and we can measure this by the level of mercury. So it's truly measuring the pressure in millimeters of mercury. So sort of convenient when we actually have liquid mercury and we're looking for a change in the distance, which is then connected to a change in the pressure. So this height of the mercury in the tube is measured in millimeters, right? Millimeters of mercury from the top of the mercury in each side of the U. So measured in millimeters from the top here is equal to then the pressure that this gas is putting out, and to then cause a pressure change as it applies pressure to the liquid mercury to cause a change in the height of the mercury. So this is for a closed tube manometer. So up here we have a vacuum. The mercury has nowhere to go, right? And the gas has nowhere to go. So it's going to put pressure on the mercury. That pressure we read out in millimeters of mercury is the pressure of that gas. So for this style manometer problem, if you see it's a closed tube manometer, then we measure the pressure of the gas as directly equal to the pressure of the mercury, or the height of the mercury. So whatever that height is in millimeters of mercury, that is the pressure of the gas. So that's our equation for a closed tube manometer. Next then, we have these open tube manometers. So notice here, this is not a closed off glass tube. This is open to the environment. It's open to atmospheric pressure. In this open tube manometer, liquid mercury in a U-tube is open to the atmosphere on one side and to a gas sample on the other side. So open to atmospheric pressure here, then open to a gas sample on the other side. As you could imagine, this pressure here from the atmosphere could be applying pressure down, forcing the mercury to go the opposite direction. So then the gas and the atmospheric pressure are sort of at odds here. If the atmospheric pressure, so the atmospheric pressure applied here, is greater than the pressure of the gas, the mercury will be higher on the gas sample side. So if this pressure from the atmosphere pushes this height down, then this level mercury will increase this direction, where then the mercury will be higher on the gas sample side. However, if the atmospheric pressure is less than the gas pressure, the mercury will be higher on the atmospheric side, right? So this gas pressure, if it's greater than the pressure that the atmosphere is applying, then this level here, mercury, will be higher on the open end side compared to the gas side where mercury is contained. The height of the mercury in the tube, again measured in this convenient unit of millimeters of mercury, right? It's a pressure. It's also directly measured by the height of that liquid mercury. So the height of the mercury is measured in millimeters from the top of the mercury in each side of the U is equal to the pressure difference between the gas and the atmosphere. Therefore, the gas pressure, which is normally what we're interested in, we're not really interested in the atmospheric pressure or what is the height of this mercury level. We're using all these components to actually measure the pressure of the gas. So this gas pressure can be calculated from the atmospheric pressure and this difference. So what this looks like is calculating the pressure of that gas in this open tube manometer. That's equal to the pressure height. So this is our unit in millimeters of mercury. It's the height of that level of mercury. So pressure height is that H, plus the pressure of the atmosphere. So usually we can measure this. Usually we know the pressure of the atmosphere. So we put these two together to then get what we usually want to find out. What is the pressure of this gas in this open tube? It's equal to the pressure from the height of the millimeters of mercury plus the pressure of the atmosphere. So for an open tube manometer problem, we would use this equation to solve for likely the pressure of the gas is usually the unknown. So we talked about using these U-tubes, these manometers, for measuring the pressure of a gas. So how do we connect this then to a volume? So in A, a gas sample is placed in a closed-end tube and mercury is added. Notice this end here is closed for the gas. So then as more mercury is added to the top of this tube, the pressure increases and the volume of the gas sample decreases, right? So once we're adding more mercury, this is going to compress the gas molecules here within this closed end of the tube. Then here, as we've applied a lot of pressure by putting a lot of this liquid mercury into a tube, we've even further compressed the gas. So the connection we see based on these images here is that as pressure and volume, they're inversely related. As we added more and more pressure, it decreased the volume of the gas. So as we added more pressure, we decreased the volume of the gas. We're going to come back to this connection between pressure and volume a lot as we deal with different variations of the ideal gas law. So we increase the pressure, the volume of the gas decreases, thus pressure and volume are inversely related. In this practice problem now, we're going to talk more about these U-tubes, these manometers, also sometimes called a J-tube because of the shape, kind of resembles a J. So in this practice problem, each sketch below shows a flask filled with some gas and a pool of mercury right here. The gas is at a pressure of 1 atmosphere. A tube is connected to the bottom of the flask that contains the gas, and the mercury can freely flow in or out of this tube. We're told we can assume that there is so much more mercury in the pool that can fit into the tube that even if the J-tube is completely filled, the level of mercury in the pool will not change. So this level here will not change. Let's keep reading through the description now. So notice that also in the left sketch in the J-tube, it's an open tube so that air from the atmosphere can freely flow in. So pressure from the atmosphere can be exerted this direction for an open tube J-tube. On the other hand, in the right sketch, the J-tube is closed at the top at its other end, and we should assume there is no gas between the mercury and the closed end of the tube. There's a vacuum here then between the mercury level and the closed end of this tube. So as you're solving this problem in Alex, you're going to slide this point here to then get the correct sketch. We must decide what the mercury level will be when the mercury finally stops flowing in or out of the tube based on the presence of gas and based on the presence of, in this case for an open tube, pressure from the atmosphere. So in solving this problem, let's go through some considerations for what we should think about when we are stating what the final sketch should look like. The J-shaped tube is called a manometer, like I've been saying, a simple apparatus for measuring the pressure of a gas. To answer this question, we need to identify all the forces on the mercury in the manometer and decide when they are balanced. So when all the forces on the mercury are balanced, the mercury is in an equilibrium with gravity, with atmospheric pressure, with the gas, and then there won't be any change in the level of mercury here when we've reached an equilibrium between all the pressures at play. So gravity is one force we should think about. Gravity is always present, but the first force on the mercury is the force of gravity. It always is going to pull the mercury down. So gravity pulls the mercury in the left side of the manometer down, making it flow from the left to the right in the J tube and then out of the flask. So we'll have some mercury pushing down here. So at the same time, gravity also pulls the mercury in the right side of the manometer down, making it flow from right to left in the J tube, and therefore back into this flask. The gravity forces will be exactly balanced when the levels of mercury on the left and the right are equal. When this level and this level are equal, then our gravity forces are perfectly balanced on the left-hand side and the right-hand side. When there are no pressure forces to consider, for example, when there is no gas in the flask and the end of the J tube is closed, then the correct answer to this problem is here. We don't have any atmospheric pressure, we just have the force of gravity. For the force of gravity, the only consideration we really need to remember is, again, when gravity is present, the level of mercury on the left-hand side will equal the level of mercury on the right-hand side. This is when we're only considering gravity as an influence of the levels of pressure here for mercury. Next now, we no longer have a vacuum, we have a gas that's present in this flask. Again, even in this vacuum, we will still have some force of gravity applied this way. It's only in a perfect vacuum that you might see in a physics class where you don't really consider gravity as an influence. For this class, for our class, gravity is still at play even within the vacuum side of this J tube. So the second force we need to think about on the mercury is the pressure exerted by the gas that's in this flask. When there is a gas in the flask, it pushes the mercury on the left side of the manometer downwards, making it flow from left to right. So gas here in this flask will cause the pressure difference to change. It'll move this mercury from the left-hand side to the right-hand side. However, the weight of the excess mercury on the right side will unbalance the forces of gravity. So no longer, if this gas is exerting pressure on the mercury, no longer do we see these levels be equal. So what's going to happen then back on this side is that gravity will try to pull the extra mercury back down this direction to then make those levels of mercury again equal. The force from the gas pressure and the forces from gravity will be balanced when the weight of the excess mercury on the right balances the force produced by the gas pressure on the left. It's hard to know when this is going to happen without this important fact here. So we need to know that a column of mercury 760 millimeters high produces a pressure at its base of 1 atmosphere. Remember the pressure conversions we looked at? 1 atmosphere is equivalent to 760 millimeters of mercury, or 760 torr as well. So a column of liquid mercury 760 millimeters in height produces a pressure at its base of 1 atmosphere. So we're going to keep this important fact in mind as we're solving our practice problem. So we talked about the gravity pressure as well as gas pressure now. So now continuation of gas pressure, here's the same fact down here. Since in this case, the pressure of gas in the flask is 1 atmosphere, we were told that in our initial practice problem here. We noticed this pressure of the gas in the flask is 1 atmosphere. So here, this pressure of the gas is 1 atmosphere. So 1 atmosphere, we know that's equal to 760 millimeters of mercury. Because our practice problem has this units of meters, we can convert this into meters. So 760 millimeters of mercury, there are 1,000 millimeters in 1 meter. So 760 divided by 1,000, that's moving this decimal point over 1, 2, 3. That's equal to 0.76 meters. That means the 0.76 meters of mercury on the right side will balance it. So 0.76 meters of mercury on the right side will balance 1 atmosphere of pressure from the gas that's present in this flask, because 1 atmosphere is equivalent to 0.76 meters. Since the pressure would be at the 1.5 meter level without the pressure from the gas, why is that again? Well, we need to make these levels equivalent. So this point here for the mercury, this was equal to 1.5 meters. So as is, this pressure level is equivalent to 1.5 meters. So since the mercury would be at 1.5 meter level without the pressure from the gas, right? This is without the pressure from the gas. This is just from gravity. It would be at 1.5 meters. But with the addition of this 1 atmosphere from the gas that's in the flask, then we're no longer staying at 1.5 meters. We need to take 1.5 meters, then account for the pressure that's in the flask, from the gas in the flask. So 1.5 meters plus this pressure that's caused by the gas is equal to 2.26 meters. This is taking into the fact that gravity causes the mercury level to be at 1.5 meters, but now from the gas in the flask, we're adding on now whatever pressure was in the flask. So that's 0.76 meters. From the gravity and gas in the flask, we get 2.26 meter level for the mercury. When there is no pressure from the atmosphere to consider, for example, when the end of the J tube is closed, right, then we know that no atmospheric pressure will be a consideration in the mercury level. So when this is a closed tube, we are only concerned about gravity and the pressure of that gas. So for a closed J tube, it's going to be, the mercury level is going to be at 2.26 meters. So that was for a closed J tube. We need to think about gravity as well as the pressure in the flask. Now we're taking the pressure in the flask as well as gravity, now as well as any atmospheric pressure, because now we're dealing for our second practice problem. Remember, that's for an open J tube. So here we solve the closed J tube. Now we're going to talk more about the open J tube. Then I will show you the final answers together for both of these cases. So when it's an open J tube, we need to consider this third component, that's the atmospheric pressure. The third force on the mercury is the force exerted on the mercury in the J tube by the atmosphere itself. When the end of the J tube is open, air from the atmosphere will be able to enter and push down on the mercury. That's going to make the mercury flow now from the right-hand side to the left-hand side back into this flask. This will be opposed by the force from the gas, though, that's pushing it this way. And if there are any unbalanced forces of gravity, we'll also encounter those, but going from this direction, also as well as this direction. We know gravity is at play on both sides of the J tube. So the pressure of the atmosphere is 1 atmosphere. That's only because we're told we're at sea level. Or we should be told we're at sea level. If we're not told we're at sea level, we can generally assume 1 atmosphere for the pressure in the atmosphere. That means the atmosphere pushes down with the same force it takes to push up a column of mercury at 760 millimeters or 0.76 meters high. Remember, so 1 atmosphere, we've done this conversion before, that's equivalent to 0.76 meters of mercury, technically. So now we have this gas in the flask that's at 1 atmosphere, that's pushing the mercury level this way. We also have 1 atmosphere of pressure from the environment that's then pushing the gas this direction. Therefore, the force from the atmosphere will be perfectly in balance with the pressure that this gas has that's in this flask. So therefore, the force from the atmosphere will be balanced with the other forces when the mercury on the right-hand side has been pushed down 0.76 meters from the level at which it would be if the J tube were closed, and if there are no other forces from the atmosphere aside from this 1 atmosphere pressure. So for our closed tube, we knew that with gravity and the gas, that this was at 2.26 meters. Now though, when it's an open tube, we now have an additional 0.76 meters or an additional 1 atmosphere of pressure pushing this direction on the mercury. So for closed tube, it was 2.26 meters. That was with gravity and the gas. Now though, when this is open, we're going to be now 0.76 meters this direction from the shear pressure of the atmosphere, where that pressure at sea level is 1 atmosphere or 0.76 meters. That means we need to take 2.26 meters, but now subtract 0.76 meters. In other words, we're only considering ultimately the pressure from gravity for our open tube because the pressure from the gas and the pressure from the atmosphere are actually the same, so they're balanced. So the pressure from the gas, 1 atmosphere, that balances out with the pressure of the atmosphere, or the atmospheric pressure, that's also at 1 atmosphere. Now the only consideration left for our open tube is gravity. From the sheer fact of gravity, we expect these levels to be equivalent. So the level here for mercury equals the level here. And again, we're no longer considering the gas in the atmosphere because those pressures are perfectly in balance. So unless we're told differently, we can usually assume the pressure of the atmosphere is 1 atmosphere. But this isn't always the case because we do have atmospheric pressure that can decrease steadily with altitude. Right, as we go up in altitude, that is a decrease in the pressure. For example, normal pressure in Denver with a high altitude is not 1 atmosphere. It's about 0.85 atmospheres. So in Denver with a high altitude, then we go back down to sea level, and then we go back up to 1 atmosphere. Also, atmospheric pressure varies by as much as 5% with local weather. Clear conditions usually mean a higher pressure. Stormy conditions usually mean a lower pressure. So here's this interesting connection between chemistry and studying weather. So in case you're interested in that, here's this connection with pressure. So now to finish solving our problem and make this connection here for an open tube manometer again, since the pressure would be at 2.26 meter level without the pressure from the atmosphere, right, just from gravity and the gas, it will now be at 2.26 meters minus the impact of our atmospheric pressure though. That's equal to 1.50. Again, we would expect this to be equivalent to, because gravity is the only remaining pressure at play because the pressure in the flask was perfectly balanced with the pressure of the atmosphere. gravity causes this level of mercury in the tube or in the flask to be equal with this level of mercury on the right-hand side of the tube. So when we do have an open tube, atmospheric pressure and gravity and the pressure of the gas are all at play. When the atmospheric pressure and the pressure in the flask are balanced, we're only concerned with gravity. This makes for an open tube, this pressure level to be at 1.5. So for an open tube, 1.5 meters, I should specify, meters of mercury. For a closed tube, again, it's going up to 2.26 meters of mercury. So only gravity and the gas were at play. Here it's gravity, the gas, and atmospheric pressure. So open tube versus closed tube. Next, we're going to start going into the different variations of the ideal gas law, the first being Boyle's law. So Boyle was a scientist that made this connection for the formula we're going to practice with. So for Boyle's law, Boyle found that pressure and volume are inversely related. As pressure goes up, volume goes down. As pressure goes down, then volume will go up. This is what we mean by an inverse relationship between pressure and volume. So here we have a plot of pressure versus volume. Remember, we always do the y-axis versus the x-axis when we're naming these. So y-axis versus x-axis, that's pressure versus volume. As volume is increasing, pressure is decreasing. For instance, we could take a look at this 0.6 atmospheres, 2 liters. We increase volume to 4 liters, that pressure goes down to 0.3 atmospheres. And sometimes it's convenient to convert these graphs to be a straight line, so we can use a slope and a y-intercept to get information from a plot. But here we have pressure and volume. Here we have pressure and 1 over volume. When we make all of these 1 over the volume, then we do get this straight line in this direction. So be careful and make sure you're looking out for what actually are on the axes. Otherwise, this could be deceptive, right? But this is pressure and volume. As pressure decreases, volume increases. Here, though, we have pressure versus 1 over volume. Here we have this straight line relationship. As we start to connect these to the ideal gas law, you'll see why these are important to note. These are at constant temperature and a constant number of moles of gas. Those are not changing, so only when either pressure or volume are changing, then we get this relationship here. If the temperature or the amount of gas were changing, then there would be other factors that are at play. Here, though, if those are constant and only pressure and volume could change, then we get to use Boyle's law that connects pressure and volume, pressure and volume. Another useful way to visualize this, pressure is inversely proportional to volume. That alpha-looking symbol there is a proportionality symbol. Pressure is proportional to 1 over volume. Also, based on these, pressure times the volume will equal a constant value. So pressure and a volume will be a constant. If we change the pressure or the volume from initially to a final set of conditions, then still this pressure times this volume equals a constant. That's still going to equal this second pressure times the second volume. So if these were our initial conditions, for example, these are our final conditions, we take pressure and volume initially, that's still going to actually equal pressure times volume in our final conditions. We'll practice using this equation for Boyle's law. So here a gas cylinder with 10 liters of gas and a piston is put into it. Here's this piston. The initial pressure of the gas is measured to be 238 kilopascals. As I'm reading a problem like this, I would probably start to label these as volume 1 or volume initially, we're told is 10 liters. Then pressure initially is 236 kilopascals. The piston is now pushed down, so we're applying some pressure until the gas has a final volume, or V2, of 6.10 liters. Calculate the final pressure of the gas. So here we're definitely going to use Boyle's law because we're given just information about volume initially, pressure initially, volume at the end, and then we're asked to solve for the final pressure. So you can label these as initial and final, or V1 and P1, or V2 and P2, whatever you want to use. So you could say volume initially or volume final, whatever notation you like to use. So from Boyle's law, P1 V1 is equal to P2 V2, or another way you might see this as P initial, volume initial is equal to pressure final times volume final. Again, Boyle's law tells us that the pressure of a gas is inversely proportional to its volume. For example, if the volume of a gas is doubled, then the pressure is halved. If the volume is multiplied by 3.2, then the pressure is divided by 3.2, etc. So 236 kilopascals and 10.0 liters. That's P1 and V1. Then we are solving for P2. We know volume 2 to be 6.10 liters. So we'll plug that in here. The only unknown now is P2. So we solve for that by dividing both sides by 6.10. 236 kilopascals times 10.0 liters divided by 6.10 liters. Liters and liters cancel out. We'll get a pressure in kilopascals. That is equal to 386.885 etc. units of kilopascals. To get this into 3 sig figs, then that would be 387, right, kilopascals. So in ALEKS, the presentation of solving this is a little bit different, but generally we get to the same equation here. So I kind of did it all in one step, but you could also break it up into steps. One very important consideration of Boyle's law is that this pressure 1 times volume 1 is equal to the same value as pressure 2 and volume 2. Because as this pressure went up, this pressure over here would have to be a smaller value, or vice versa. So always P1 V1 will equal the same constant or same value as P2 V2. To prove this, P1 V1 is equal to 236 kilopascals times 10.0 liters, multiplying this by 10, moving the decimal place over then once. That's what P1 times V1 is equal to. Now let's see if this holds. What's P2 times V2? So 387 kilopascals, like we just calculated, multiplied by 6.10 liters, the second volume. So 387 times 6.10 is equal to 236.0.7. With some of the rounding we did, these do indeed equal each other, aside from the minor rounding. So this is, again, a very important consequence of Boyle's law. The pressure of the gas times its volume does not change because of what we saw with Boyle's law. The pressure of the gas times the volume, again, does not change. They both still equal this same value here because, again, as something went up, the volume went up, this had to go down. As this pressure went down, this pressure had to go up. Then again, our final answer here, 387 kilopascals. There are some additional practice problems, again, in the main slide deck, per usual. Example 5.5 should directly relate to another example using Boyle's law. Next, we're going to use Charles's law. So in Charles' law, we are connecting the gas volume with a temperature. Again, as we get into the ideal gas law more, you'll see why it's important that this is at constant pressure now and constant number of moles of gas, or constant amount of gas. So to observe these changes, a small sample of gas is placed into a capillary tube at a low temperature. Mercury is added to the tube. This very skinny tube here, this small tube, is called a capillary tube. You can use it to find the melting point of different solids. The benefit of it being so small is that you don't need that much sample. If the sample is precious, expensive, hard to make, then again, that's a benefit because these capillary tubes have such a small diameter. Then when the temperature increases, so we're increasing the temperature of this whole system, while the mercury in the tube stays the same, that means we're at constant pressure. The mercury in the tube stays the same. We're going from a low temp to a high temp. What happens to the volume as we increase the temperature? As temperature increases, pressure stays the same. The amount of gas stays the same. What this leads to is an increase in the volume. Now, these are considered temperature increases, volume increases. So temperature and volume are now directly proportional. Remember, for Boyle's law, pressure and volume were inversely proportional. Now for Charles' law, temperature and volume are directly proportional, temperature and volume. I'll get to a slide at some point in chapter 5 that does summarize all these different gas laws or versions of the ideal gas law, including Boyle's law, including Charles' law. So let's visualize now Charles' law, also sometimes paired up with Gay-Lussac's law, because they work together for a lot of these experiments. So here's volume on the y-axis and temperature on the x-axis. Again, we're focusing on how the volume directly correlates to temperature when a gas is at constant pressure. Because they're directly proportional, then as the temperature increases, volume increases as well. This makes sense too, because we think about those gas particles being heated, they're experiencing more kinetic energy. So as they're heated, they are expanding, they're moving about more, so they're increasing the volume that they occupy. For the ideal gas law and for all of these gas law equations, be sure to convert everything into Kelvin. As a reminder for conversion into Kelvin, this should be degrees in Kelvin plus 273.15. There's an extra decimal there. I will definitely delete on the version of the slides I post for you. So for slide 31, we know how to go from Celsius into Kelvin, take the temperature in Celsius, and add 273.15. Get very comfortable with this temperature conversion as we go into chapter 5, because we want to more often than not work in Kelvin. So these two scientists worked together. They both found that when pressure was constant, the volume of a gas sample decreased as temperature decreased, as long as the temperature is measured in Kelvin. So we increase temperature, we increase the volume, we decrease temperature, we decrease the volume. For all gas samples, the volume of the sample approaches 0 liters in volume as the temperature approaches 0 degrees Kelvin, or equivalent to negative 273.15 degrees Celsius. As we get very, very cold temperatures, extremely cold temperatures, absolute 0 temperature, then for all gas samples, it makes sense that their volume approaches almost nothing. Their volume approaches 0 liters. Now for Charles' law, the connection we want to keep in mind, volume is now directly proportional to temperature. So volume is directly proportional to temperature. Recall for Boyle's law, we had pressure is inversely related or inversely proportional to volume. That was for Boyle's law. So that was the 1/, we saw here. Now though, for Charles' law, these are directly proportional. Volume and temperature, I should say specifically, are directly proportional. Now how this works out is that volume is equal to a constant times the temperature. This holds for final and initial temperatures as well as final and initial volumes. Now for Charles' law, the equation you're going to want to remember, use, write on your note card, V1 over T1 is equal to V2 over T2. So now we have a connection between pressure and volume from Boyle's law, now volume and temperature from Charles' law. Let's do this practice problem. We have Arctic weather balloon is filled with 2.34 liters of helium gas. I would probably instantly start writing that volume initially, 2.34 liters. The temperature inside the shed is at 9 degrees Celsius. I would notice this right away and plan to convert this into Kelvin either right away or definitely throughout the problem. The balloon is then taken outside where the temperature is now, 6 degrees Celsius, that's our T2. We also will definitely need to convert that into Kelvin, so plus 273.15. Calculate the new volume of the balloon. And again, we need to keep in mind, are we taking V1 over T1 equals V2 over T2? It's a little bit different than Boyle's law, right? Where for Boyle's law, we took P1 times V1 is equal to P2 times V2. So just keep all these equations very clear. So we know for a volume and temperature style problem, we're going to take V1 over T1 is equal to V2 over T2. And again, the very first thing we want to do is convert these into Kelvin. So 9 plus 273, you'll see it as either plus 273 or plus 273.15 to take degrees C into Kelvin. So 9 degrees C, 282, 6 degrees C, 279. So this is 282, this is 269. Oops, this should be Kelvin. Both of these are Kelvin now. So again, in Charles' law, it tells us that the volume of a gas at constant pressure is directly proportional to its absolute temperature. What this means by absolute is we need to convert this into Kelvin. Kelvin is our absolute unit of temperature. So absolute 0, that's when we're talking about temperature being in Kelvin. So it's absolute temperature, units of Kelvin. For example, if the absolute temperature of a gas is doubled, then the volume is also doubled. If the absolute temperature is multiplied by 0.8, the volume is also multiplied by 0.8, and so on. And again, it can't be said enough, we don't ever want to work in Celsius and Fahrenheit, generally in all of Chapter 5. We want to convert into Kelvin by adding 273 or by adding 273.15. Usually just adding 273 will get us a temperature that is going to lead to a correct answer. To be safe, we could add 273.15. We should get very close answers regardless of what temperature conversion we use to go between degrees C and Kelvin. So we're going to use V1 T1 over V2 T2, or V1 over T1 is equal to V2 over T2. Then we plug in the volume and the temperature, but in Kelvin. Oops, this should be 279 Kelvin. Sorry about that. So 6 degrees plus 273 is 279 Kelvin. So not 269, but 279 Kelvin. So as we're setting this up, our only unknown is V2. And again, Alex is solving it in a slightly different way. I like to set it up as Charles' law and plug in what we know, then solve for whatever unknown is left. This means we would take this, all this multiplied by 279 Kelvin to cancel that out, saying that volume 2 then is equal to 279 Kelvin multiplied by 2.34 divided by 282. That's equal to about 0.008297. I would keep this full number in my calculator, multiply that by 279. Doing that, I get equal to 2.315, etc. Our units here I should have kept in. This is liters over Kelvin. Then Kelvin and Kelvin cancel out, leaving just liters, which is what we want for a volume term. All right, we want that to be in liters. To get this into 3 sig figs, then V2 would be equal to 2.3 2, right? This 5 bumps this one up in units of liters. So Charles' law tells us the final volume, or VF, or what I've been using is V2 of the gas equals the initial volume V1, or V1 multiplied by the exact same number. Where does this come from? Well, volume is equal to a constant times temperature. To rearrange this, then our constant would be equal to volume over temperature, right? Divide both sides by T. V1 over T1 was equal to 0.008297 liters over Kelvin. Then V2 over T2 have to equal that same number. V2, 2.32 liters, T2, 279 Kelvin. This indeed is also equal to 0.008315 in units of liters over Kelvin. So yes, indeed, this does check out. That is an important point about using Charles' law. So volume over temperature is some constant. Volume over temperature has to be that same constant. You might also see it written like this: volume is equal to a constant times temperature. Just rearranging that, we get a constant is equal to volume over temperature. So that's one way to check our answer here in solving for V2. So we got 2.32 from the work we did on this slide to rearrange Charles' law and solve for V2. So indeed, 2.32 liters is our final answer for that volume using Charles' law. We'll go through more ideal gas law equations in the next part of chapter 5. I hope you're all doing well. I will talk to you very soon.